dx. Okay, so to evaluate this integral, doing u substitution, well, it's not important, but I'll raise this to a power of 5. Okay. All right, so to evaluate this integral, we can do a u substitution. And so the way that works is I'm going to choose something to be u. And what I'm going to do here is I'm going to choose u to be this expression that we have in the parentheses in the denominator. So u is x cubed minus 3x squared plus 4. Okay. So we pick something to be u, and then what we need to do is we also need to compute the derivative and get du. Okay, so here getting the derivative of u, so derivative of x cubed is 3x squared. This will be minus 6x. And then the 4 becomes 0 when we take the derivative. So du should be 3x squared minus 6x dx. All right. Now, looking inside the integral right now, so we can rewrite this integral in terms of the variable u. So in the denominator, this would become u to the 5th power. Now, what we also need to do is we need to also rewrite everything in the numerator in terms of u as well. So the way we do that is we make use of our du equation down here. So notice that if I were to divide both sides of this equation by 3, so we would get 1/3 du equals, and here dividing by 3 will leave x squared minus 2x. And then dx. Okay. All right, so it just so happens that the expression that we have here, x squared minus 2x dx, that's the same as what we have up here in our integral in the numerator and then with the dx. So using this last equation, I can replace these two with 1/3 du. And so with the 1/3, since it's a constant, we can put it in the front of the integral. And then the du, we'll put it at the end of the integral, like that, okay? Okay, so now we've managed to change variables from x to u. And so now what we'll do is we'll evaluate this integral in terms of u right now. So in order to evaluate this integral, what we can do is we can first rewrite it. So 1 over u to the 5th is the same as u to a power of -5 du. And then using the power rule, we can evaluate this by, so the rule was to add 1 to the exponent, so it'll become -4. And then dividing by -4. And I'll go ahead and put a plus c now since I've already integrated. Okay. And then lastly, what we want to do is we do want to rewrite our answer in terms of the original variable, so in terms of x. So we need to plug this back in for u. So let's see here. Let's multiply the 3 and then -4, so we'll get -1/12. And then we'll replace u with x cubed minus 3x squared plus 4. And we had u raised to a power of -4. And then plus c. Okay. And then that would be a good place to stop for the problem. If you wanted to do one more thing, what you perhaps could do is move this term into the denominator, since it has a negative exponent, we could move it down as x cubed minus 3x squared plus 4 to the power of positive 4, and then p. Okay. All right. So I would say either of these two expressions would be acceptable as like a final answer. Okay. All right. So that was just a quick example of doing U substitution. All right. So do you guys have any questions about that right now? All right. Yeah, so I'll be doing a couple of more examples with U substitution. All right, so let's just take a quick look at how the procedure works though. So we need to choose something in our integral to be our U. And then whatever we choose for U, we need to compute du. Okay. So maybe when I get to integration by parts, then I can try to address that question. All right. Okay, so we choose something to be U. We need to compute du. And typically the way that your U substitution problems will work is, whatever you choose for U, you'll see something resembling its derivative in the integral as well. And so the idea is you'll be able to get rid of that bit using your du equation, okay? So that's kind of like maybe one way to try to determine if you want to do U substitution. If you can identify something in your integral whose derivative sort of appears to be in the integral as well, that might suggest that you would do a U substitution then, okay? Yeah, all right. So let's do another example right now. This time, let's do a definite integral. So I have the integral from 0 to 1 of x e to the x squared plus 3 dx. All right. Now for this example, so it's a definite integral, and when you have a definite integral and you're doing U substitution, there's kind of two ways that you can go about evaluating it. So I'm going to go ahead and kind of illustrate both methods. They're both okay. You can use whichever one you prefer. But what I'm going to do is I'm going to start by doing my U substitution. So in this example, what do you guys think you would choose for U? Okay, so x squared plus 3 is going to be a little bit of a better choice. So whether you choose x squared plus 3 or just x squared for U, your du is going to be 2x dx. But the benefit in choosing U to be x squared plus 3 rather than just x squared is that it simplifies the integral that you get when you're writing it in terms of U. So with U being x squared plus 3, the exponential would now just be e to the U. Exactly, right? So usually when you're picking something for U, if you have like extra constants like a +3, you may as well include that into your u just because it's just going to go away anyways when you compute du. And it's going to make your integral look a little bit nicer afterwards. Okay, now let's see here. So I still have the x dx in my integral that I need to get rid of. So we can do that using our du equation. So here dividing by 2, we see that 1/2 du is x dx. Okay, so we can replace the x and the dx with a 1/2, which I'll put in the front, and then a du, which I'll put at the end. All right. Okay, now, since we had a definite integral though, what you could do right now is you can solve for the new bounds in terms of u. So that's the first rule about a definite integral. Doing u substitution. So let's kind of go over how that works. So originally, when we were integrating with respect to x, we had bounds from 0 to 1. So to get the bounds on u, what I want to do is take these two values for x, and I want to plug them into here to get the corresponding values of u. So if x is 0, u is going to be 0 squared plus 3. Okay. So that will give me the new lower bound with respect to u. And then looking when x is equal to 1, so u is going to be 1 squared plus 3, which will be equal to 4. And that will give us the new upper bound in terms of u. Okay. So let me go ahead and finish working through this problem. And then I'll also talk about how you could have done this another way without solving for the new bounds. All right, so to evaluate this integral, so first the integral of e to the u du is just going to be itself. And now what we're going to do is, after getting the antiderivative, you need to plug in your bounds. So we're going to plug in the 3 and the 4. So if you guys remember how this works, you plug in the upper bound. So we're going to plug in 4 for u. And then you're going to minus what you get when you plug in the lower bound. So plugging in 3 for u gives us minus 1/2 e cubed. Okay? All right, so any questions about this example so far? All right. Okay, now something else that you could do for this problem though is when you do the u substitution, what you can also do is instead of solving for these bounds in terms of u, you can evaluate this integral as being 1/2 e to the u. And what you can do is convert back to the original variable x. Whoops. So in terms of x, this would be 1/2 e to the x squared plus 3. So if you convert back to x at the end, then what you can do is just apply the original bounds, which were in terms of x. So if we do that, plugging in 1 for x will give us 1/2 e to the 4th. And then you'll minus what you get when you plug in 0 for x. And plugging in 0 for x gives us e cubed. Okay. So as you see, it gives you the same answer either way, whether you solve for the new bounds in terms of u, or whether you switch back to x and then use the original bounds. Okay? All right. So either way should be acceptable. So you can sort of just pick the one that you prefer to use and go with that. If you really want like a definite answer which method to go with, sometimes what I suggest to students is that you use the method that you see your professor using. So if your professor seems to always switch to the new bounds and like all the examples that they do, then perhaps you would follow their lead and do that in your problems as well. But really, you should be able to do either method and you should be fine, okay? Now, regarding whether you could simplify this answer, you can simplify a bit. So yes, you can factor out a 1/2. You could also factor out an e cubed from both terms. That will leave us with an e in the first term and then just minus 1 in the second. So you could factor it like that. Okay. All right, great. Let's see here. Okay, I'm going to do one more example of u substitution for now. Okay. So in these two examples that we've seen, so it works is you pick something to be u, and then it just so happens that the derivative of u, up to like some constant multiple, the derivative of u appears in the integral as well. So you're able to sort of get rid of that by using your du equation. Sometimes it's not so immediate or obvious when you have your integral presented to you at first. And what you might need to do is a little bit of manipulation to get it into a place where you can actually do a u substitution. So here I have this example. It's the integral of cosine cubed. So if we were to try to choose something for u right now there's maybe not that much to go with. If you were to try to choose u to be cosine, for instance, your du would then involve a sine. Let's see here, 1/10. Let me look at that. Oh, yeah, that's right, yeah. But what? All right, so let's see here. Let me go back to the previous example real quick. And then, yeah, let me put 5 in there. Okay. All right, so would you be able to explain how you are getting those numbers? I think you're off by, oh, I see. So you integrated again is what you did. At least that's what it looks like to me.
Okay, I'm gonna talk real quick, sorry.
Yeah.
Like since those are the bounds,
Uh-huh.
because when you just did the u substitution,
Mm-hmm.
you end up with 1/2 e to the u du when you do the u sub, right?
Yeah. Mm-hmm. Mm-hmm.
After that, you need to, don't you have to like
integrate it.
Integrate it again.
Yeah. Yes.
So, like,
So yeah, when we get the half and then the integral e to the u du, so we do have to integrate it again. But what's the integral of e to the u du though?
oh, it's e to the u. Okay, sorry.
Yeah, that's right. Yeah.
Okay.
Yeah, but I see what you did. Yeah. Okay.
Okay. I just wasted everyone's time. Sorry. Okay,
No,
bye.
no, no. No problem. Okay. Always happy to answer questions that you guys have. So yeah, don't feel bad about that. Yes. Yeah. Okay. Very good. All right. So let's take a look at this example here. So one thing that you might consider if you were to try to do a u sub is to choose u to be cosine, but the issue with that would be that du involves a sign, and you don't have any signs in your integral. So doing this for your u substitution is not exactly going to work. But since we see that it looks like it might be useful to have a sign in our integral before we do a u substitution, that suggests that we might try to rewrite this using a trig identity. Okay, so what I'm going to do here is I'm going to rewrite cosine cubed as cosine times cosine squared. Yeah, all right. And then here I'm going to use a trig identity. So the Pythagorean trig identity says that cosine squared of some expression data, and then plus sine squared of the same expression data equals 1. Okay. So in particular, that tells us that cosine squared is equal to 1 minus sine squared. So in my integral, what I'm going to do is I'm going to rewrite the cosine squared of 5x as 1 minus sine squared of 5x. Okay. So now that I've done that, I'm going to do another u substitution attempt. All right, so what do you guys think you would choose for u now? Yes, okay. So sine of 5x is a good choice. That is going to work. So let's see how that works. So if a u is sine of 5x, okay, so we need to compute du, which would be 5 cosine of 5x. All right. So rewriting this integral in terms of u, okay, so first 1 minus sine squared would become 1 minus u squared now, okay? Okay, so that takes care of this portion. And then cosine 5x dx, we can get rid of using the du equation. So we see that 1/5 du is cosine of 5x dx. So we can replace cosine 5x dx with a 1/5 du. And now that we've converted it into the new variable u, we need to finish out this integration here. So the integral of 1 minus u squared du would be u minus u cubed over 3. Okay? And now what we'll do is we'll just replace u with sine of 5x. And then that would be the final answer for this problem, okay? All right, but what I sort of intended to illustrate is that sometimes you need to do a little bit of work at first before you can apply your u substitution to it, okay? All right, any questions about this? Okay. All right, so what I would like to do right now is I would like to just give you guys one exercise to work on. So I'm gonna give you guys an integral and we'll give you guys a little bit of time to work on it, and then we'll go over that integral together after that. Okay. Let's see here. So I have two integrals, but I think I'll give you guys the one that's a little bit easier. Okay. Okay, so let's take a look at this integral. So let's give you guys 1 to 2 minutes just to think about this problem, maybe try to work it out on your own, and then we're gonna go over it together after that, okay? All right, so we'll pause for 1 or 2 minutes. You guys work on this problem, and we're gonna come back to it after that. All right, so I'm going to have one of the students or student workers helping us to present this problem. So Julie, why don't you take this one over?
Okay, great. So can everyone hear me okay? Assuming yes. Awesome. Okay. So I'm just going to really quickly rewrite this problem on the whiteboard, and then we'll talk about how to solve it. Okay, so you have the integral of x times the natural log of x squared plus 1 divided by x squared plus 1 dx. So the first part about this, obviously this is all about u sub. So what did you guys pick as u? Any ideas in the chat? It was a little bit more challenging. Okay, so I'm seeing a lot of x squared plus 1 and a lot of natural log of x squared plus 1. So one of those is correct. So I would say you want to pick the one that has the derivative that's present in the integral. So if you pick the natural log of x squared plus 1, the derivative of this, du, is going to be 2x over x squared plus 1, which is something that's pretty present in your integral. You have an x over x squared plus 1, which is good. This means we can simplify this integral by rewriting everything in terms of u and du. So if you pick this as u, you can replace this whole thing with u, and then you can replace the rest of it with du after you take out the 1/2. So we're going to rewrite this as 1/2 times the integral of u du. Does everyone see how I got that? Any confusion on how we got there? Basically, I picked the harder thing as my u, and then I made du equal to 2x divided by x squared plus 1 by taking the derivative, and then I just rewrote that as u du after I took out the 1/2. So 1/2 du would be. So now this simplifies pretty easily. You're just left with 1/2 times the integral of u du, and from here it just becomes a really simple integral that we all know how to solve. So the integral of u just becomes 1/2 u squared, and you also have to remember that you have a 1/2 that you pulled out from the front originally, and so you're going to have the new integral of 1/4 u squared. And at this point, you're just going to go back and you're going to replace your, So if you chose u as x squared plus 1, you would basically just have to do it twice. So to keep it simple, you should pick natural log first because you have the derivative in your integral. So then you can just go back and replace your u with what you replaced it with originally. So then your final antiderivative should just be 1/4 the natural log of x squared plus 1, that whole thing squared, plus c. So the hard part about this is just making sure you pick the right u. Again, if you picked x squared plus 1, you just have to do like a little bit of a longer process. But in general, it's good to try to see what u you should pick where you have the du present in your integral. So in this case, du being 2x over x squared plus 1, that's something that I can pretty evidently see in my integral. And so it was just easier to pick this as your u. But this is your final antiderivative that you end up getting. So any questions on that or clarification that needs to be made? Would it need to be natural log of absolute value of x squared plus 1? Not in this case because you're just picking if Elliot wants to further clarify on that.
Yeah, so there's a couple of reasons why we don't need the absolute value. I guess actually first it's just because you have x squared plus 1 inside your natural log. So since that's always positive, that's right. So that's one reason. Other reason though would be, so what you're thinking of is, and let me switch back to my OneNote real quick. Okay. So the other reason is you're thinking of the rule where if you're integrating 1 over x dx, that it becomes natural log of absolute value, right? Okay, but that was a little bit different from what we were doing in our problem. So we started with natural log without an absolute value, and we made that our u. And so because I guess the problem started with natural log without an absolute value in it, then that means like it would carry over without an absolute value at the end as well. Okay. So just maybe another quick example of what I'm kind of talking about. Let's just say if I had integral natural log of maybe just 3x over, oh, this might be interesting. So let's do 3x over x. All right, so for this problem, we can do another similar u sub, u being the natural log. And then here, du would be, let's see here, 1 over 3x, but then times another 3 from the chain rule. So it would actually just be 1 over x dx. Oh, and actually, I'll tell you what. This would be better if okay, I think this would be more fun if I put the natural log in the denominator. So I'm going to change my problem slightly. Okay. Okay, let's consider this. This would be more fun. So if I choose u to be the natural log still, so that means we get a u in the denominator. And then the 1 over x dx, all of that together will just be replaced with a du. Okay, so here we have the integral of 1 over u du. So integral of 1 over u du should be the absolute or natural log of the absolute value of u. Okay. And then when we're plugging in u, well, u was natural log of 3x without an absolute value. So when we plug in u, it's going to be natural log absolute value, but then we'll have like natural log without an absolute value of 3x plus c. Okay. So when you're integrating like a 1 over u or 1 over x, you'll pick up a natural log with an absolute value. But if you started with a natural log in your problem and you're choosing that to be like a u for u sub, you don't need to like add absolute value onto it later. All right, so then I don't know if that answers your question well. Does that make sense? Okay, awesome. All right, so let's take some time talking about integration by parts next, all right? Okay, so to motivate the problem, let's consider this integral up here first, all right? So I had the integral of e to the power of square root x dx. And what I did with this integral is I started with a change of variables. What I chose to do for this is I made the change of variables x equals t squared. Okay. So then square root of x becomes square root of t squared, which I simplify to be t. And then if x is t squared, then dx is 2t dt. So I replace the dx with a 2t and a dt. Okay. So that's a little bit of an unconventional change of variables, but that is something that we can do. But now that we've made this change of variables, we're left with this new integral. And this integral, if you try a couple of things for u, you'll find that u substitution doesn't quite work for this example. So to evaluate this integral, we need a new technique, and a technique that will handle this integral is integration by parts, all right? So I'm gonna go over the idea of integration by parts. Then we're going to finish working out this integral. And once we work out this integral, Then we'll do a couple more examples of integration by parts as well, okay? So here, the idea of integration by parts comes from the product rule for derivatives. So I've written out what the product rule is here. So it's a uv prime is u prime v plus ub prime. Okay. So I'm going to take the product rule and I'm going to rearrange it a little bit. So what I did was I subtract the u prime v term to the other side. So that uv prime will equal the derivative of the product, and then minus u prime v. Okay. So I moved this term to the other side, and then I just rewrote it a little bit. Okay, so from here, what we're going to do is we're going to integrate both sides. So I integrate uv prime. I integrate the uv prime over here, and then integrate the u prime v over here. Okay, so I apply the integral to everything in this equation. All right, now, if we rewrite v prime dx as dv, then this becomes the integral of u dv. Now over here, when you integrate a derivative, remember that the integral and derivative, they kind of cancel each other out. So this entire integral just becomes ub. And then here, the u prime dx, those two together, we're going to call that du. So this becomes the integral of v and then du. Okay. So this is the formula for integration by parts. Okay. And so I'm going to apply the integration by parts formula to the integral that we have up here. So we'll see how it works, all right? So the way it works is we choose something in our integral to be u. And I'll talk about how to determine what you want to choose for u, but I'll do that later. For now, I'm just going to go ahead and choose u. And for this problem, I'm going to choose u to be 2t, okay? All right. So we choose something to be u, and then everything else in the integral is going to be your dv. Okay, so remaining in the integral, we have e to the t dt. I'm going to call that dv. Okay. So we have u dv. Okay. Now I'm going to compute du by computing the derivative of u. So derivative of 2t will be 2, and then I'll put a dt at the end. And what I'm going to do is we have dv. I'm going to integrate dv to get v. Okay. So integral of e to the t dt is just e to the t. All right. So we choose something for u and dv. Then we get du and v from that. And now we're going to apply our integration by parts formula. So starting with the integral of u dv, which we have, we can rewrite that as uv. So u is 2t, v is e to the t. So uv, and then we have minus the integral of v du. So that's coming from this part over here. So v was e to the t, and then du was 2 dt, and I'll put the 2 on the outside. Okay. All right, and so starting with this integral, we managed to rewrite it as this. And then this integral is one that we can easily evaluate. So that will become just another e to the t. And then I'm going to copy down the 2t e to the t that we had in front. Okay. All right, so then that gets us the answer to the integral of e2t e to the t. So the last thing I might do is over here. If I wanted to switch back to the original variable x, I would just rewrite t as square root of x and plug that in over here at the end. So replace t with e to the x. So then this will give us the final answer for the integral of e to the square root of x dx, all right? Okay, so I wanted to start with this example just because I liked how it started with a change of variables, which is what we talked about earlier, and then how it then involved integration by parts afterwards, all right? So any questions about this example right now? Okay, so I'm going to talk a little bit more about integration by parts, and I'm going to do a couple more examples of it as well. So let's go over the procedure for integration by parts. So the idea is in your integral, you're going to choose something to be u. And then whatever you choose for u, everything else in your integral will be dv. Once you decide on what your u should be and what your dv will be, you'll need to compute du by differentiating u, and then you'll need to compute v by integrating your dv, okay? Once you have u, du, dv, and v, you'll then rewrite your integral using this integration by parts formula. Okay. So that's just a rough outline of the procedure. Now there's a useful tool for deciding on what you should choose to be your u when using integration by parts. So I'll go over that right now as well. Okay. So there's a acronym for determining what to choose for u. I think that's the right word. So the acronym is ILATE. So the I stands for inverse trig. The L stands for logarithms, so such as the natural log. The A stands for algebraic. just maybe a little non-descriptive. I'll talk about that. T stands for trig, and then E stands for exponential. So that would be something like e to the x. Okay. And so this acronym gives you sort of the order of priority on what you should choose for your u. So if you have an inverse trig function in your integral, and you're going to do integration by parts, then you would choose u to be the inverse trig function. If there's no inverse trig function in your integral, but there is a log in your integral, then you would choose that to be your u instead. If you have no inverse trig or log, so algebraic refers to, basically refers to things like polynomials or powers of x, a bit more generally. So things like that are typically what we mean by something that's algebraic. So that would be your next choice for u if you don't have any inverse trig or log functions in your integral. And it's somewhat rare that you would choose u to be a trig function. And you almost never choose an exponential to be u since it appears at the end of this, okay? So I'm going to do a couple more examples of integration by parts. Yes, There you go. Okay, so I'm going to take a look at the following example first. So let's consider the integral of x squared minus x and times the natural log of x. All right. So looking at this right now, if you think about doing a u substitution, what you'll find is that you can't really choose anything for u in such a way that your du, its derivative, appears inside the integral. So u sub is not going to work on this problem. Now, what we can do though is we can do integration by parts instead. So right now, between the two expressions that I have in the integral, okay, if I follow this guideline on what to choose for u, the logarithm, the natural log, takes precedence over the algebraic expression, x squared minus x. So for u, I'm going to choose u to be the natural log then, okay? And if u is the natural log, then the dv must be the x squared minus x dx instead, okay? All right, so then we'll compute du, which will be 1 over x dx. And we need to integrate dv to get v. So the integral here would be x cubed over 3 and minus x squared over 2, okay? All right. Okay. So then we have the integral of u dv on the left. So using the integration by parts formula, we're going to rewrite this as uv. So that would be u is the natural log, and then times v, which was x cubed over 3, minus x squared over 2. So uv, and then it's minus the integral of v du. So v is, again, x cubed over 3 minus x squared over 2. And then du was 1 over x dx. Okay. Okay, so now we have another integral that we need to evaluate, but this is an integral that we can evaluate relatively easily. So what I'll do for this is we'll distribute the 1 over x into the parentheses. So that will just cancel out an x from both terms, leaving us with x squared over 3, and then minus x over 2. Now from here, we can evaluate that integral now by using the power rule. So let's see here, x squared over 3 is going to become x cubed, and then over 3 times 3 will be 9. And then minus, and this will be x squared over 2 times 2, so over 4. And then I'll put a plus c now at the end, okay? And then that would have been the final answer for the integral. All right, so any questions about that? All right. Let's see here. I have quite a few examples. I think I'm going to do this one next. Okay, so let's consider the integral of arctangent of x and then dx. Okay, so looking at this integral right now. So at first glance, it might not seem like you can do integration by parts, because with integration by parts, you need like a product of u and dv in your integral in order to apply this formula. And right now, it looks like we don't really have a product perhaps inside of our integral because we just have an arctangent. Okay. But you can always pretend that inside this integral, that's arctangent of x times 1 dx. So even if you just have one thing in your integral, you might be able to use integration by parts anyways. Okay. So let's try to use integration by parts on this. So remembering ILATE, if I'm going to do integration by parts, my first choice for u would be an inverse trig function if there are any. So arctangent is an inverse trig function. So I should choose that to be u. So that will leave the 1 dx as my dv. Okay. So we have our u and our dv. So du, the derivative of arctangent. So remember that was 1 over 1 plus x squared. And then here the integral of 1 would just give me an x. Okay. So now let's apply the integration by parts formula. So we have the integral of u dv. So we can write that as being equal to u times b and then minus the integral of v times du. So v times du, I'm going to put that x in the numerator. All right. So then integration by parts gives us this new integral over here. But now this integral is one that we can evaluate with a u substitution. Okay. So if we choose u to be the 1 plus x squared, then du would be 2x dx, which I have in the numerator x and then dx. So if I divide by 2, then I see that we can rewrite everything in the integral as, let's see here. So I guess I'll continue writing the x arctangent in front. Okay, and then here for the integral, with our u sub, that's going to be 1/2 u in the denominator, and the x dx became the 1/2 and then a du. All right, so let's finish this up. So integral of 1 over u du will be natural log of absolute value of u. And then we'll replace u with 1 plus x squared. I guess since it's always positive, you could drop the absolute value. Although it would be okay to leave it as well. That would technically still be okay. All right, so then that will leave us with the final answer for the integral of arctangent. Okay. Any questions about that? Okay. So I think what I'm going to do here is I'm going to give you guys another integration by parts example to work on. It's like another exercise. And then after that, I'll just touch on trig substitution. And I'll try to do just at least one example of trig sub. And then we'll end the workshop at 2:30. All right, let's see here. Okay, so I'm going to give you guys this integral of, let's see here, 3x plus 2 is your sine of x dx. Okay, so why don't you guys take a couple of minutes to think about this problem and try to work it out with integration by parts. And then again, we're going to go over it together afterwards. Okay, I think that's good enough. So even if you're not finished, at least you spent some time thinking about the problem, so I think that's good. So Luke is going to go over this problem with you guys. All right, so Luke, you can take it from here.
Thanks, Elliot. Hey guys, I'm Luke, and we're gonna do this integral. So we have the integral 3x plus 2 times sine of x, and then we have our order of precedence for picking u, isolate. And as you can see, we have quote-unquote algebraic right here. That is a polynomial of degree 1 coming first. So we're going to choose that for u. And then we also have a trig, but that comes after in the acronym. So let's choose u to be 3x plus 2, and then we calculate du. Du is just 3 dx. And then what's remaining is dv. dv is sine of x. Don't forget your dx. And so what is v? Someone tell me what v is. That's right. It's actually negative cosine. Negative cosine. And you can always check your work on this, right? We integrated sine, and so the derivative of cosine is negative sine, so the two negatives would turn back into a positive. And then, so we have our formula, uv minus the integral of v du. And a little mnemonic to help you remember it, ultraviolet voodoo. So if you're on an exam and you can't remember what the formula is, it's ultraviolet voodoo. So we're going to do UV minus the integral of v du. So we have minus a negative cosine times 3 dx. So that turns into a positive 3, the integral of cosine x dx. All right, so what's the integral of cosine? Yeah, positive sine. So we have 3 sine x, and then the rest of it. And so what is the only thing that I'm missing? Yep, that's right, plus c. Very good, y'all. Thanks.
All right, great. So with the time remaining, I'm just going to touch on trig substitution, and I probably have time for probably just one example. Okay. So with integration by parts, you can see some more complicated examples, ones which may involve doing integration by parts more than once. But I didn't have time to get to that, but I think that's okay because I just wanted to introduce the technique to you guys. All right, so finally, let's get to trig substitution. All right, so trig substitution, it's basically a change of variables involving a trig substitution. Okay, so it's based off these Pythagorean trig identities. So we've already seen the first one, cosine squared theta plus sine squared theta equals 1. If you take this equation and if you divide it through by cosine squared, so cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent squared, and 1 over cosine is secant, so it would become secant squared. Okay. So you get this second trig identity by dividing the first one by cosine squared. Likewise, if you divide the first one by sine squared instead, you will get this third identity down here. Cotangent squared plus 1 is equal to cosecant squared. Oh, whoops, that's right. My bad. I forgot to reshare. Okay. All right, cool. Okay, yeah, so I was just going over these Pythagorean trig identities. So the first one we've seen before, divide this equation by cosine squared. It gets you the second identity here. And if you divide this first one by sine squared, it gets you this third identity. Okay. Now this third identity, at least I personally seldom use this third one. So I would say it's maybe not super important. If you just remember the first two, you're probably going to be good. Okay, so I have here a couple of expressions starting with the square root of a squared minus x squared. So I wanted to illustrate what would happen if we made the change of variables x equals a sine theta. Okay. So if we were doing an integral, then we would need to compute dx, which would be a cosine theta d theta. Okay. But looking in particular at what happens when we replace x with a sine theta. So x squared would become a squared sine squared. And if I factor out the a squared from terms, we get 1 minus sine squared remaining. So 1 minus sine squared is cosine squared, according to this identity. So then when we square root a squared cosine squared theta, for trig sub, you'll be able to simplify that as a cosine theta. No problem. And yes, question? Okay, all right. Yeah, no problem. Okay. So whenever you have a square root of a squared minus x squared in your integral, doing this change of variables will simplify it to just be a cosine theta. So that can help in simplifying your integral into something you can work with. Likewise, if you have x squared minus a squared in the square root in an integral, if you do x is a secant theta, and if you plug that in for x and use this trig identity, you'll find that it simplifies to be a tangent theta. And finally, if you have the square root of a squared plus x squared in an integral, if you make the change of variables x equals a tangent theta, then again, that will simplify fairly nicely. So that's kind of the idea of trig substitution, is whenever you have expressions like this one, or this one, or this one, then making one of these three trig substitutions could help in simplifying the integral. So I'm just going to do one example illustrating this. I'm going to try this second one over here. It is kind of like U substitution, yes. It's just a sort of a specific type of U sub or change of variables where you're typically using a trigonometric function for that change of variables, okay? Oh, whoops. All right. So I had 3 examples prepared, but I only have time to work through one of them. So I'm going to work through this one here. All right, so let's see here. In this integral, we have a square root of 1 plus x squared in it. Okay, so that resembles this situation here. If I have square root of a squared plus x squared, with my a being equal to 1, okay, to get 1 plus x squared. So looking at this, it looks like I should make the change of variables x equals 1 tangent theta, or just x is tan theta. So then dx would be secant squared theta d theta. Now that square root of 1 plus x squared should simplify to be a secant theta, where a is 1. So with this change of variables, I should get a secant in the denominator where the square root was. Okay, so that takes care of the square root term. Now, as for this x squared term, we can replace x with tangent theta. So x squared will become tangent squared. And then the dx in the integral will be replaced with a secant squared theta d theta. Let's see here. I'll put the secant squared on top. So dx is secant squared theta, and then d theta. All right. So after doing this trig sub, we're left with a new integral over here. Let's start simplifying it. So first, I can cancel out a secant from numerator and denominator. So it's just going to be secant over tangent squared. Okay, and to evaluate this integral, I think what I'm going to try doing is I'm going to try to rewrite all of this in terms of cosine and sine, because I don't see anything at the moment I can really do. So sec I know is 1 over cosine, and tangent is sine over cosine. Okay. And here I'm dividing by a fraction, so I'm going to rewrite this as multiplication by the reciprocal. So instead of dividing by sine squared over cosine squared, we're going to multiply by cosine squared over sine squared. Okay. So with that, I can now cancel a cosine from the top and bottom. Okay, so I think that looks pretty good. So that leaves me with a cosine on top, and then a sine squared on the bottom. Okay. All right, so this integral we can do with a u sub. So I'm going to do u is sine, and then du will get rid of the cosine in the numerator. So let's see here. Cosine theta d theta will just become du. And then sine squared is u squared. So if we rewrite this as u to the -2, all right, so integrating that will give us u to the -1 over -1. So u to the -1 over -1, I'm going to rewrite like this. Okay. All right, now we're not quite done yet, so I do want to first rewrite u as signed data. But there's one more thing is I started the integral in terms of x, so I'd want to rewrite my answer in terms of the original x rather than leaving it in terms of data. Okay. So in order to do that, yeah, okay. So 1 over sine, we could rewrite that as cosecant. Oops. All right, but we still want to rewrite this in terms of x. So here's how we're going to do that. It's going to be based off this trig sub that we did, x equals tangent data. So I'm going to come over to here for that. So what I'm going to do is I'm going to draw a right triangle to help me out. So I've drawn a right triangle and I've labeled one angle as theta. Okay, now remember that from SOHCAHTOA, remember that tangent is opposite over adjacent. So I'm going to label the opposite side as x and the adjacent side as 1. And then you could get the hypotenuse using the Pythagorean theorem. It would be square root of 1 plus x squared. And now from this triangle, I just want to rewrite cosecant of data in terms of the sides of this right triangle. So cosecant was 1 over sine. So sine is opposite over hypotenuse. So cosecant should be the reciprocal, so it should be the hypotenuse over the opposite. Okay. So that means cosecant data, we could rewrite it as hypotenuse, so 1 plus x squared square root. All right, and then over the opposite, which is x. Okay. So then that's how you can switch back to the original variable when you do a trig substitution. So if you draw a right triangle, it can help you out in doing so, all right? All right, so we're gonna go ahead and wrap up the workshop with that as being the last example. All right, so we have a little survey that we would like for you guys to fill out just to get some feedback on what you guys thought about the workshop. So if you guys could fill out that survey, it'll only take maybe 2 or 3 minutes at the most. Yeah, okay. I'll go back to the Trig Sub formulas.
Thank you all so much for taking the time to put this on. Really appreciate it.
No problem. Thank you.
Alrighty. Have a great day.
Yeah, you too. Julie, looks like everyone has left, so I don't know if you have some questions about tomorrow's stuff. I could try to answer them.
Okay, yeah, I was just wondering if like tomorrow's workshops are going to be like today's, where like we spend a lot of time on review and then do like a few examples. Because I was looking at some of Les's stuff and it's just like all example problems. So I was just wondering if like
Yeah.
we're going to go through all of them.
I would guess he's not going to work through all of them, but I think you'd have to ask him for more specifics on exactly what he's going to do.
Yeah, okay.
I know for sure there's no way that he would actually get through all of that in the time that he has. So
Yeah, I figured. But it's
yeah.
just kind of right into like the actual solving of problems and stuff. And so I was wondering if we were just gonna like spend most of that time doing all those problems.
Yeah, so I'm not sure.
I'll probably just send them an email or something and ask for some clarification on that. So no worries, but thank you.
Oh, sorry, I got muted somehow, but yeah, that's okay. Yeah.
Okay, thanks. Bye.
All right, bye.